Every single second, trillions of invisible data packets surge through the air and under our feet, completely unseen. To most of us, this massive system is just an abstraction. We interact with what computer scientists call the services view, a programming interface that provides software hooks, allowing applications to easily send and receive data. Take a distributed application like Skype. When you start a video call, the software simply grabs a transport hook, assuming the internet handles the delivery. But beneath that clean interface lies the nuts and bolts view. This is the physical reality, a sprawling, chaotic infrastructure of billions of connected computing devices, packet switches, and communication links. To truly understand how a network functions, we have to look past the glowing screens. We have to deconstruct this invisible software abstraction layer, layer by layer, down to the physical hardware. The bridge between your software's intent and that physical hardware is called a protocol. In computer networking, all communication activity is governed by strict rule sets. Protocols define the exact format and order of messages sent and received among network entities, as well as the specific actions taken upon transmission and receipt. Think of a human protocol. One person says hi, the other replies, and you ask for the time. A computer network protocol operates identically. A machine sends a TCP connection request, gets a response, and issues a GET command for a file. Because millions of different devices need to communicate, these rules are heavily standardized globally. Organizations like the Internet Engineering Task Force publish these standards as RFCs, or requests for comments. Just as grammar dictates how humans parse sentences, protocols provide the rigid, universally understood syntax that allows a smartphone in Tokyo to seamlessly load a web page hosted in New York. If we want to trace a protocol message from its origin, we have to start at the outer boundary, the network edge. The edge is populated by hosts, also known as end systems. These are the clients making requests and the servers providing the data. This diagram shows where these end systems sit in relation to the broader internet. They exist at the absolute outermost perimeter of the architecture. It is exclusively on these perimeter hosts that distributed applications, like our Skype example, actually execute. Historically, this perimeter was made up of bulky desktop PCs and enterprise servers. Today, the definition of a host has expanded rapidly. We now see an influx of non-traditional connected devices running network apps right at the edge, from smart speakers and security cameras to sensorized mattresses. The edge is the vital boundary layer. It's the exact location where human interactions are digitized, packaged into protocol messages, and prepared for transport. Once an edge device formats a message, it faces a physical problem. How does that isolated host push its data out to the rest of the world? The solution is the access network. This is the initial physical on-ramp that connects an edge device to the very first router. Looking back at our diagram, these black dotted lines trace the physical connection pathways leaving the hosts and traveling to the local switch. These represent actual, tangible communication links, bridging the physical distance between a transmitter and a receiver. Engineers categorize physical media into distinct types: guided media traveling through solid materials, and unguided media propagating through air. Because all data must pass through these initial links, access networks act as a critical physical bottleneck. The medium you choose dictates the absolute maximum speed your data can travel before it even reaches the wider internet. Let's look closely at guided media. The most common type is twisted pair copper wiring, which we universally know as Ethernet. Ethernet is the dominant technology for wired local area networks. It's highly reliable, cost-effective, and simple to install inside office buildings and homes. However, it is bound by the physics of electrical resistance. Modern Category 5 to Category 6A cables typically offer transmission rates ranging from 1 to 10 gigabits per second. When greater bandwidth is required, networks switch to fiber optic cables. Instead of pushing electrical currents through copper, fiber uses a thin glass core to carry rapid-fire pulses of light. Each pulse represents a single bit of data. This shift from electricity to light yields massive performance gains. Fiber offers speeds well over 40 gigabits per second, maintains high security, and can transmit signals across oceanic distances without severe degradation. But what if you need mobility? That requires unguided media, where signals propagate freely via radio waves, the foundation of wireless LANs or Wi-Fi. Wi-Fi provides convenience within a radius of about 100 feet, maxing out around 450 megabits per second. To break that distance barrier, mobile operators deploy wide-area cellular networks, like 4G and 5G, pushing data across tens of kilometers. Whether it's copper, glass, or radio frequencies, the engineering choice of physical media establishes the hard boundaries of physics. No matter how efficient a software protocol is, it can never exceed the bandwidth and range dictated by the physical link it travels on. Let's track our data as it successfully crosses the access network. It now leaves the local environment and enters the heavy infrastructure. This diagram shows the signal moving through the local router and up into the vast space we call the network core. The core is not a single entity, it is a network of networks, a massive, globally interconnected mesh of hardware. The engines driving this core are packet switches, primarily consisting of heavy-duty routers and high-capacity switches. These machines have one strict mechanical function: to take chunks of data, called packets, arriving on one communication link and forward them out onto the next appropriate link. Unlike the devices at the edge, these core machines do not run user applications. They don't initiate requests or consume media. The network core is entirely blind to the user's intent. Whether you are sending a text message or streaming video, the core's sole relentless physical purpose is routing those packets closer to their final destination. To see how a packet actually navigates this maze, we have to zoom out and look at the macro topology of the system. The architecture is strictly hierarchical. Millions of home and enterprise networks feed into local and regional internet service providers. Those regional ISPs then aggregate massive amounts of traffic upward into national and global ISP backbones. Trace the full journey. A protocol packet originates at an edge host, crosses the local access switch, and pushes through the local gateway into a core router. It is then handed off across the high-bandwidth links of the ISP hierarchy, eventually terminating inside a massive data center, the content provider network where the destination server resides. The smooth, seamless cloud we imagine is actually an illusion. The reality is a meticulously layered geographical hierarchy of physical hardware, exchanging data point to point. This is why understanding the internet requires a top-down deconstruction. It begins with a simple, abstract user action at the services layer, clicking a link or launching an app, which instantly triggers a strict, mathematically precise set of protocol rules. Those rules are translated by edge hosts into sheer physical energy, bursts of electricity and flashes of light, pulsing across access networks and high-speed core routers. To master computer networking, you must see past the software interface. You have to recognize the rigid, beautifully engineered system of physical wires, switches, and glass fibers, executing in perfect, silent sequence underneath.